So, good, recording now. So, welcome back. Next lecture, we're going to start into the meat of some physics. We're going to start into something called kinematics. This is the study of motion. Just like when we talked about units and we talked about measurement, we talked about needing a standard. So we're going to kind of continue that idea that we're going to need a standard for talking about motion. So we know we're going to use our standard units. We know we're going to talk about meters. We know we're going to talk about seconds. But we have to come up with a couple of different terms that we're going to use. So I made a list of them here. You don't really necessarily need to copy these down, but you need to be familiar with them. And the more you work on the homeworks and the more we do problems in class, you're going to become very familiar with these. But there are a couple of them. These are a couple of big ones that you're going to see, and I want you to really understand what they mean. So the first thing that we're going to talk about, the term that we're going to talk about, is position. Now, when I say position of an object, I will use the term object or particle interchangeably. In this course, it really doesn't matter. We've just got a thing that is represented by a mass, so we're going to call that a particle. A lot of times you will hear physicists talk about a spherical cow in a vacuum. And that's because anything that we do, we're going to represent as a single particle with mass, and we're not going to care about its shape. We're not going to care about things like air resistance. We're not going to care about things like friction for the most part. So any object that I make might as well be spherical, might as well be in a vacuum, and because I don't care about shape, might as well be a cow. So spherical cows and vacuums is how we're going to talk about this. So let's say in terms of position, I have my spherical cow in a vacuum, and I need to locate that cow. Now, we talked about in one of the other lectures, when I started talking about units and started talking about decimal places and nearest 10,000, 10,000, etc., that you might think about that as math coordinates. So you might think about the campus as the whole number of places, and a decimal, the first decimal might represent this building, second decimal might represent this classroom, and so on down. Often we're going to need to talk about the position of things in terms of some arbitrary form. This is a place where we're going to use a lot of knowledge that you have gained in terms that you've heard and things, skills that you've done throughout your algebra career up to this point, but now we're actually starting doing something with it. One of the most common things that I get from students, especially if I teach an entry-level mathematics course or something, when I used to teach high school, I would get, well, what are we ever going to do with this? Why do I ever need this? Well, physics is where we're going to start answering all those questions. So the first skill there that we're talking about is this idea of your standard graph. Remember in Algebra 1, you were doing things with graphs and you were saying, oh, okay, if something is at x1, y3, then you can pick that on the coordinate system. So that's where we're going to start. So position can be described in some coordinate system. Every coordinate system is going to have an origin. It's going to be the center. Now, for all of your algebra classes, you kind of think of the intersection of those two axes as the origin and the 0, 0 point. Here's where physics is going to get a little weird, but it's also going to make your life a whole lot easier. There is absolutely nothing that says your origin has to be at the 0, 0 point. There's absolutely nothing that says that your map of where this particle is has to be this kind of XY plot. It can be whatever is convenient for you. Now, the first few things we're going to do, if we think about this XY plot with the origin in the center, that is going to be totally sufficient. So if I want to talk about the position of a particle, just like in algebra, I need to know an XY coordinate. So we're going to say this is X, this is Y. We are also going to talk about positive and negative. But all this means is that the positive and negative direction are largely arbitrary. We get to choose as physicists what the positive direction is. For example, when we start talking about objects in free fall, if I drop a ball off the top of the building, it is perfectly acceptable to make down be the positive direction. The reason you want to do that is because generally in physics terms, we talk about acceleration due to gravity as being in negative in direction. Well, you're going to have a negative floating around all over the place. And so if I ask you to do things like calculate how much time it takes for this ball to reach the ground after you drop it, if we count the Y, if we count down as the negative direction, you're going to get negative seconds, which is perfectly okay in a physics context. We just have to understand where those vectors are coming from, where this direction. We'll talk about vectors a little later on. But in order to make my life easier, I can just say, well, down is the positive direction. That doesn't mean that you have to swap your X direction same way. You can leave that alone. So it's perfectly fine. Have a coordinate system looks like that. Doesn't matter. The point is, we need to be able to define where our particle is. Where is our spherical cow? If we pick some arbitrary origin, then we can say it is a number of units this way in the positive direction and a number of units this way in the negative direction, regardless of what direction that is. Nothing says that you have to orient this coordinate plane the way you normally draw it. There is absolutely nothing wrong with making a coordinate system that looks like this on kind of an angle. And as we get into more complicated things, you're going to see how this will make your life extraordinarily useful. Because obviously, if I'm going to do this, I need to think about kind of how far I've tilted that thing, how far I've rotated it, and in what direction. There are going to be problems that we're going to encounter where we're going to need to account for that. And because we can set our coordinates to wherever the hell we want and whatever orientation we want, we can exploit that to make these problems better. So the point here, though, is to understand the kinematics term. The origin is just wherever you're going to start measuring from. Your origin doesn't have to be 0, 0. Origin can be -1, +5 if you want. Whatever makes sense for the problem. The position is simply where that thing is in reference to your coordinate system. Everything we're going to do in here. I think everything we do in here is 2-dimensional. It is possible to have a 3-dimensional coordinate system. So if you want to think in terms of cube, we might have an X, a Y, and a Z direction. So length, width, height, if you like. This is what we call dimensionality. Sometimes you will hear me talk about dimensionality, or hear another physicist talk about dimensionality. So if I talk about something as 2-dimensional, 3-dimensional, 4-dimensional, this is what I mean. This is how many sets of points that I need to describe the position of that certain power. Much later, if you progress in physics, as far as I have, once you get into towards your senior year, or expect to once you get into graduate school, you're going to start working problems that are n-dimensional problems. What happens if you have an object in a 6-dimensional space? Now, what the hell does 6 dimensions look like? I don't know, but we can certainly model. We're not doing that in this class. We're only worried about 2 dimensions. We're worried about an X and a Y. Displacement is a little bit different. Displacement is where a lot of students tend to get kind of wrapped up. Let's say I have some standard coordinate system with my origin at 0, 0. And we'll say moving to the right here is positive X, and moving up is the positive Y direction. If I walk, let's say this is, my house or something, that's the origin, and I walk a mile in the positive X direction. Starting to see what I'm talking about, how this is arbitrary. Notice I didn't say the positive X direction had to be take a right turn on my front door, or a left turn, or climb a ladder, or whatever. It's just some arbitrary direction. I have chosen the direction that I'm going to start moving is going to be the positive X direction. Cool. The position I'm at in this case is going to be 1, 0, obviously. Now, if I make a turn and I go and I walk, say, 2 miles in the positive Y direction, my position there is going to be 1, 2, obviously. Now, here's where displacement comes. What I want to know is how far away from the origin am I? How far away from home am I? This is a pretty simple example. Where is it? You might be tempted to say, well, this is 1 mile, and this is 2 miles, so that my total is 3 miles. That is incorrect. That is a distance you have traveled, for sure. Displacement is not total distance traveled. Displacement is total distance from the origin. We're going to call that D. One of those weird physics terms I talked about last week, where we will use letters over and over again to mean different things. In geometry, you might have seen D represent diameter. Well, in this case, D is going to mean displacement. Anytime I talk about a distance, generally I'm going to use D, or you're not going to like this. Sometimes we use S. S is not speed in this case, it's displacement. Doesn't really matter why. And again, you just need some context. And as you go through working problems, you'll figure out what makes more sense to use. These are just the standards. It does not mean that if you are more comfortable writing displacement as a smiley face, you can do that. But keep in mind that I have to understand what your system is too. Little aside on that, I used to teach programming in high school. And I had a student who was a pretty decent programmer. She also loved cats. It was cool because I love cats. And she would name all her variables after cat breeds. So there would be a variable called calico, and there would be a variable called Maine Coon. And then there might be a subroutine that was called Himalayan. Well, they meant something to her, but I could not decipher her code because I didn't know what that meant. And she explained her naming convention to me, which is fine, it works. But without a standard frame of reference, really hard for us to talk to each other. So that's why as physicists, we tend to use E or S for displacement. So our displacement is the distance away we are from the origin. Well, this is pretty easy to figure out because we've got a two-dimensional coordinate system. We can certainly just use the Pythagorean theorem. This is just a right triangle, right? So there's your displacement is your hypotenuse. If this is 1 and this is 2, notice we're using the same units in miles. As long as these units are the same. Now, be careful because it is fair game on an exam for me to do something like I walked a mile this way and 300 meters this way. And which miles and meters you have to know which one's which. So you're going to have to convert one of those units so that they're both the same to do this. But once you do that, then just basic high school algebra tells us that the square root of this, or the square of this side is the square root of the sum of the squares of the two other sides. It's a right triangle. And thus we can find our displacement. In this case, 1 squared is 1, 2 squared is 4. So root 5 is what? A little more than 2. So our total displacement is a little more than 2 miles. A lot of times, the way that we're going to express our displacement is going to be through change in position. Right? So think about that. Displacement is the distance from the origin. It is also a way to express the change in position. So a lot of times what we'll do is we'll say displacement we might say displacement in the x direction. So that might be d sub x, s sub x. You're going to see this kind of notation. This can also be delta x. This is a notation you're going to see a lot when we talk about the change in something. So the change in the x position in this case. So the way you get that is you take your final value minus your initial value. So in the case of I'm walking away from home, if we take that first leg where I went 1 unit in the positive x direction, I started at the origin. So my initial is the origin. My initial x position is 0, and my final x position is 1. So that means my delta x is 1 minus 0, which is just 1, and that's what we expect. You can do the same thing in the y direction. Or the z direction, whatever coordinate system you happen to be using. Just the key thing to remember with this notation is delta always means final minus initial. You're going to come across times, particularly in physics 2, when we start talking about voltages, we start talking about resistances, currents, that kind of thing, you're going to find that knowing this relationship is going to be extraordinarily helpful to you, because you're going to be able to write things in terms of deltas and then expand it out, and suddenly things are going to cancel in fractions and make your life a whole lot easier. For now, nothing crazy like that. Just think with the delta notation as final minus initial. So that gives you change. Finally, I want to talk about the difference between speed and velocity. A lot of times in our daily lives, we will use these terms interchangeably, and that's not entirely true. Speed is a matter of distance per time. So that's what we're generally going to call it. Now, I know last time I said velocity is distance per time, and I'm going to tell you why that's actually a more correct statement. So speed, we can think about something like driving down the interstate at 70 miles an hour. Cool, that's definitely a speed. You have a meter in your car called a speedometer. That doesn't measure how tight your swimsuit is. That measures your speed. So speedometer. All that tells you is how fast you're going. What distance per time are you covering? Velocity is almost the same thing, except it has a directional component. So if I'm driving my car and you're going to tell me how to get to Conway, you might say, get in your car and drive at 70 miles an hour. Fantastic. So I'm just going to pick a direction and go, right? So I may never get to Conway. You have to tell me a direction. Conway is relatively north of here. So you'd say, okay, you need to get in your car and you need to drive 70 miles per hour to the north. Okay, now we're making more sense. Now I'm going to get closer. So this is where this positive and negative stuff comes into play. If I'm going 70 miles an hour, I need to know what direction. Am I 70 miles an hour in the positive direction? Am I 70 miles an hour in the negative direction? This is where you're going to get confused doing some of these problems, because you're going to come out with velocities that are going to be negative. So your initial thought is probably going to be, well, how can I go negative 70 miles an hour? Means I'm going back in time or something. Well, no, it doesn't. It has to do with displacement and position. So your velocity then, erase some of this. Your velocity then becomes the change in position over the change in time. Since our delta is the same thing as final minus initial, normally any calculation we do, we're going to start our clock at 0, because why wouldn't you? It seems a little silly if I'm going to measure how long it takes me to walk to the chow hall. When I say, okay, ready, set, go, it makes no sense for me to tell you to start your stopwatch at some arbitrary time. And then whenever I say go, look at your stopwatch. If it's 14.5 seconds, that's where we start from. So yeah, you see, I have to subtract that 14.5 seconds off when I get to my destination. Pretty tough. So we're just going to call our start time, our initial time 0, 99% of the time. And so any number obviously is going to be positive because we can't go backwards in time. Any positive number minus 0 is going to be a positive number. However, for our x position, our delta x, remember, our coordinate system is what we chose it to be. it is certainly possible that you can get a delta X that's negative. So I might just start and I might end on the other side of the origin from where I started. That's okay. And so what you end up with is a negative value on the top, positive value on the bottom. Basic fractions tells you that's a negative value. That negative value, remember, is just direction. I will say this often in this class. In physics, a negative sign generally indicates direction. Don't be scared when you start seeing values come up that are negative, especially in these first couple of homework assignments. The ones that I put up that should show up on website today are going to deal with this stuff. You're going to end up with a lot of answers where it's going to ask you to express a velocity or a position and indicate direction with sign. So be careful what direction that you choose as your positive direction. Generally, we pick up as positive, but again, when we're doing free fall problems, we'll find that it's much more convenient to say down is the positive direction. I know that's kind of strange from the way you normally think, but again, it will really help you. So velocity in physics, we generally use V with this little arrow above it. That means it's a vector. We're not going to dig too deep into vectors in this class. I will mention some things about vectors that are more calculus based that will help you understand this, but I'm not going to hold you responsible for the calculus stuff on the exam because I cannot be guaranteed that any of you are even going to have calculus. The bad news is not knowing calculus and relying only on algebra like this course does makes some of the physics pretty tedious. And some of the equations are tedious to get through. Not terrible, just takes you a longer time than if you could do it with calculus. For example, there are some problems that we're going to do that might take us 3 or 4 lines to do with algebra. If I knew calculus, I could do them in one step. So little things like that. So this is what we're talking about. Whenever you see this little arrow over a variable, whether it be a velocity or an acceleration or even a position, we're talking about a vector, meaning that it intrinsically has a directional component, so it's going to have a sign. So it's important to keep track of positive and negative. Does anybody have questions so far about that? Because I'm going to go in and walk through the notes here if you guys don't. Okay. Stand by one and let me slides. All right, so these are the notes that I post on Blackboard. And I generally will post these as we start covering new material. These are the notes that go along with the textbook that I recommended to you in the syllabus that should be free to you. If you have noticed doing the homeworks that if you encounter a problem in the homework, if you miss a question, a lot of times it will give you a reference to the textbook. This is the same textbook these slides are built from. So it's a good idea, even though I may not always go through every single one of these slides in class, it's probably a good idea to read through those because that's where this is coming from. It's going to give you a lot of good examples. It's a good way to have a reference when you're working on the homework. So let's take a look at this example. Just by seeing my slide, should say figure 2.3, right?
Yes, sir.
Okay. So here we have our standard coordinate system we're gonna say that our Y direction is positive up. And the X direction is positive to the right. Notice, this is a case where we did not choose the origin to be the intersection of the X and Y axis. Well, we did, but we didn't choose to start our measurement from there. We chose here, it looks like we chose an arbitrary origin. And the instructor's starting position there on the left happens to be 1.5 meters away from the origin in the positive X direction. And then she's going to walk a couple of steps to the other side of the board. And we happen to note that that position in respect to the origin is 3.5 meters. So doing what I just showed you, if you'll notice at the bottom of that graphic there, it shows your X naught. Sometimes we'll call that initial instead of X sub I like I wrote. A lot of times we'll use X sub 0 or X naught. Is 1.5. Our X sub F or X final is 3.5. So remember our delta is final minus initial. So our X minus F or our X sub F minus X sub naught should give us 3.5 minus 1.5. You should be able to work that in your head that that's positive 2.0. So that's 2 meters of displacement in the positive direction. Pretty simple.
I'm so sorry, but all we can see is like the college physics slides.
Oh, really?
Yes, like the notebook.
Yeah.
Well, I see both, but well, it went away now.
Yeah, I stopped share for a second.
I think it's when you talk,
Yeah.
we see your board, we see the whiteboard, but when you stop talking, we don't see the whiteboard.
Oh, I see. Okay.
But if you guys go to the bottom of the screen, just click on that small picture. It'll switch yours to the whiteboard, and you can see what he's sharing as well. I don't know. It's kind of confusing.
Yeah.
Yeah, now I can. Yeah,
Zoom.
now I can see both.
Okay. Yeah, so you should see something that says John Anglin, and I think that's where you're seeing the whiteboard.
I
And
see the whiteboard.
Also got a shared screen. That's my slide.
Yeah, I see the slide and the whiteboard.
I
Okay.
just see the slides. I don't see the whiteboard.
Okay. Well, I'm done with the whiteboard for now, so it doesn't really matter. I should have a better solution for this next week. Like I said, I'm working on some technology solutions to make this flow a little bit easier. All right, so here's our displacement slide. This is another example. We've got an airplane here, and some dude has stood up to walk to the back of the airplane. And I'm really curious what airline this is. These people have this much leg room. That does not look like any 767 I have ever flown on. But anyway. So we'll see that we choose some origin. Again, some arbitrary 0 point that's somewhere after the aircraft. And we said, well, he started in a seat that was up towards front of the airplane that was 6 meters away. So that's going to be our origin. And he ends up at a place that's 2 meters away from this origin. He walked back towards the back of the airplane. So that means our displacement is going to be a negative 4 meters. Okay, remember displacement negatives are just directions. So that's all we're doing here, nothing crazy. So here's our coordinate system we were talking about. Notice I can set my coordinates anywhere I want. And here's a little bit more complex diagram. So we've got this airplane passenger heading towards the back of the plane, but we've broken it up into smaller segments. So this delta X sub A might indicate that he was sitting up in first class, drinking free whiskey, lucky bastard. And he gets up and he walks towards the back of the airplane, some short distance. We're going to call that delta X sub A. And then from there, he walks a little further back. We can call it delta X B. Then for some reason, he moves back towards the aircraft. So notice the arrow points in the other direction. Delta X C goes to the right. Then he turns around, goes all the way to the back. Delta X sub D. And then our delta X total, notice what we're doing is we're adding all of those things. So our delta X total there is going to be our delta X A plus our delta X B plus our delta X C plus our delta X D. Remember, your deltas are going to have direction. So our delta X A, B, and D are all going to be in the negative direction. And our delta X C is going to be in the positive direction. So when you start doing this in homeworks, pay attention to that. Keep track of your signs. In this case, our total displacement is certainly going to be a negative value because we're going to the left or towards the negative direction as we've chosen our coordinate system. And that's okay. Here is another interesting example about displacement. So let's say that I need to go to the store. I start at my house and the store is 3 kilometers away. So I move towards the store 3 kilometers. And let's just say from my house to the store is the positive X direction. So I move 3 kilometers in the X direction. Get what I need. I try and I come home. Following the same path, I now move 3 kilometers in the negative X direction. So my total displacement here is not 6. The total distance traveled is certainly 6 kilometers. Because remember, just plain distance, don't really care about a direction. But displacement I do. So I have to account for the negative sign. So what you end up with is positive 3 kilometers plus a negative 3 kilometers, which is the same thing as a minus 3 kilometers. So you get 3 kilometers minus 3 kilometers gives you 0 kilometers. So our displacement here is total of 0. This is a concept that's going to help you out tremendously when we start actually doing calculations. You're going to be able to exploit this in a couple of things and go, well, I know that my total displacement is 0, especially when we start talking about energy. The energy required to accelerate a ball upwards, for example, if we throw it, you're going to have to put some energy in. You're going to have to work against gravity. Well, where does that energy go? It goes into the ball and it's got to come out if the ball's going to come down. So the total energy of that whole system from the time you threw the ball up until the time you caught it again is going to be 0 because of that displacement factor. So keep that in mind. I think this is where I'm going to stop today. Wednesday, I'm going to pick up talking about these graphs. These graphs are, you're really going to get beat up on these in the lab. And you really need to understand these things. Once you can understand how to do this, though, once you understand how these graphs work, it is going to make your life way, way easier. I have put these up on Blackboard already. Notice that there's 67 slides in this deck. Obviously, I'm not getting through them all today, not going to get through them all tomorrow. It'll probably take me till Friday to get through all of these. That's okay. But you can read ahead if you want and be a little more prepared for this, which is fine. All right. And I think that is where I'm going to stop. Does anybody have any questions, comments, concerns, or smart remarks before I quit?
Nope.
Yep. Okay, so remember, get working on the homework. It is in your interest to make an attempt and start doing the homework as soon as they get published, because you are going to get behind really fast in this class if you don't stay on top of it. And if you get behind, it's going to be really hard to catch up. So stay on top of the homework, reach out to me if you need help. I'm actually here on campus today until about 5 o'clock. I'm in ETAS 300E on the hallway with the rest of the physics department. If anybody needs me, I will be around all day. All right. I will see you guys next time, same bat time, same bat channel.